Okay, so this next chapter is about solving systems of linear equations. So this chapter is a bit of a standalone in terms of this course because it's not necessarily related to one specific kind of function. So just to outline what we're going to do, the first part of the chapter we're going to be devoted to talking about different solving techniques. So solving by graphing, substitution, elimination, and then we'll talk about some matrix methods. If you don't know what a matrix is, it's not like the movie some years ago, but it is a very useful mathematical object that makes life potentially quite easy. And then after that, we're going to talk about some applications. So it turns out there's lots of places where solving a system of equations or a system of linear equations is really interesting or applicable. So one would be writing the standard form equation for a quadratic. Just from 3 points. We can have a geometry application that is mostly about matrices, but we can talk about the area of a triangle. And then we'll just do some general kind of story problem situations. So this is just kind of the overview of what we're going to do in this chapter. Again, it kind of helps in the beginning if we kind of know in general what it is that we're going to be doing and why we're kind of going in that direction. And really the reason why we sequence this chapter immediately following the quadratics is I want to address this question of how we can write the standard form equation for a quadratic given just some points on that quadratic. Because that's not entirely clear how we could do something like that if we didn't know the vertex. Or didn't know like the x-intercepts or something. Like if we don't know anything about the specific points we're given, not entirely clear what we would do. Okay. So, again, we're going to start with solving techniques, and the first one we're going to start talking about today is graphing. But probably before we talk about that, we should talk about what we mean by a system of linear equations, right? So when we say a system of equations, we're talking about a set of equations, like 2, 3, 4, 5, 6 of them, whatever, that have to be true simultaneously. What that means is that if we find a solution for that system, that solution has to satisfy all of the equations. So, little quick example here. So the way we'll write a system is with, just like two equations in a row like this. And usually we include this like big curly bracket in front of them to show that like all these equations need to be taken together. So this solution, or this system has the solution 5, -5. Never mind how I've gotten that. Just what I want to do is demonstrate what we mean by both equations being true simultaneously. What that means is if I substitute that answer, or that solution, into the first equation, that works. And if I substitute it into the second equation, we see that that also works, right? So what we mean when we say a solution to the system is we want, a set of solutions, like a value for x, y, z, etc., depending on how many variables we have represented in our equations, where when I plug them back in, those solutions satisfy all the equations in my system. Is everybody okay with that as an idea? Okay. So the most pertinent question then is, how do I find that solution, right? We've identified like what a solution looks like, and it's easy enough to check that what we have is a solution, right? All we need to do is plug it back into all the equations and kind of just check. But how do we find that solution? And that's what the bulk of this chapter is going to be concerned with. There are some different ways to find that solution. So we'll start with maybe the most intuitive one. So let's talk about solving by graphing. And we'll just kind of do this as an example. And I'm going to use that same system that we had written above. So what my plan is for this is I'm going to graph both of the equations in the same set of axes. Okay, so on the same xy axis, I'm going to graph both of these two equations. And then I'm going to look at what I have. Okay with that plan? So in order to graph a linear equation, what would make life a little bit easier? Well, if they're in y equals form, right? If they look like y equal mx plus b, that would make life a little bit easier, right? So the first thing I'm going to do is rewrite them in that form. So from the first equation, I'm going to subtract 2x from both sides. And in the second equation, I'm going to subtract x from both sides and then divide by -1. So far, so good? Okay. So, to graph a line, these are both linear equations, right? They look like y equals mx plus b. To graph a line, how many points do we need to have? 2. Okay? So, from the first equation, I'll write that in blue. I'm just going to pick 2 values for x. Should I pick these 2 values of x right next to each other or kind of far apart? I'm going to kind of pick them far apart. The reason being, because we're graphing this, neatness is going to matter. And the further apart I am, if I'm like a millimeter off, that's not a big deal if the 2 points are very far apart. If they're right next to each other, if I'm a millimeter off, that can really create a big problem. So there's no mathematical reason to pick the points far apart. It's a purely like, I have to draw this on a sheet of paper and neatness is going to matter a little bit to me reason to graph them far apart, or to pick points that are kind of far apart. And when I say kind of far apart, I don't even have like really anything in mind. So I'm just going to pick maybe 0 for x. When I plug 0 in, I get 5. And maybe I'll pick 5 for x. And when I plug that in, I get -5 for y. Bless you, bless you. Zero and 1, yeah. I mean, if you're very neat or you're doing it on graph paper and using a ruler, probably fine. If you're doing it loosely by hand with scales you've drawn yourself and you're not the neatest kid on the block, I would not do it that way. Again, just from a practical standpoint of actually having to draw these things. Now, certainly there's nothing wrong with picking those 2 points. Like, they're legit points. Like, you certainly would make the same line. But in terms of, like, practically drawing that same line, it's a little bit more difficult. Or any inaccuracy kind of gets amplified. So I'll do the same thing here. Maybe I'll just pick 0 for x. That gives me -10. And maybe I'll pick 10 for y. That gives me 0. So I have enough information now to graph. Hi, Christian. Thanks. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay. So I'll start by plotting the first one. I have 5, or 0, 5, and then 5, -5. And I'll draw my line. Ideally speaking, if you're doing this by hand, what would you want to use there to draw that line? A ruler would help. Again, like, does it have to have a ruler? No, but from a practical concern, it certainly makes it easier to draw a straight line if you have a straight edge to use. And then I'll do the same thing. So I'll plot 0, -10, and then 10, 0, and I'll draw my line. And recall, what did we say was the solution to this system? Was 5, -5, right? Which we notice is here. So what are we going to be looking for as far as a solution if we're graphing? I'm going to be looking for where they intersect. Are you talking about this spot here? When I plug 5 in for x, -2 times 5 is -10, and then plus 5 is -5. So I pick the x's and then I find the y's by plugging them in, just like we've done in the previous chapter. Okay? So, important question becomes, well, how many solutions can I be looking for? So we've seen the situation above, right? How many solutions did we have here in this first example? 1, right? We had 1 intersection. So we can certainly just get 1 solution as a possibility. What else could happen? What would that look like? Yeah. We could have infinitely many solutions. And what Marshall's saying is if I graph, and this is my first line, and then if that's my second line, how many intersections do I have? Infinitely many, right? At every point on the line, those are intersecting. So that's a possibility. What else could happen? I'm surprised we came up with the infinitely many before this second, or before this one. That's usually the last one students can think of. So good job there, but there is one more situation we can run into here. What if something like this happens? Yeah. What do we call those 2 lines that we've drawn in that? That's the word parallel. Okay. Now here's the catch, or the nice, maybe it's not the catch. Here's the nice thing. So right now we've only been considering a situation where we had like 2 variables, an x and a y, right? This same thing holds regardless whether I have 2 variables or 25 variables. You're either going to have 1 solution, infinitely many solutions, or no solution at all. So whether we're dealing with a 2-variable system or a 25-variable system, this still kind of holds. Now, the amount of detail we can do or we can use to describe those infinitely many solutions changes there a little bit, because it turns out that we can actually describe the nature of those infinitely many solutions. Now, it's silly to do that in 2 variables because it's just the equation of the line, that they both make is the description of the infinitely many solutions. But in 3 and 4 and 5 and 6 and whatever variables, there we can be really specific about, like, hey, if you have this value for x, then you can find, you know, like this would be your y, and then this would be your z, and this would be whatever. And we'll talk about how to do that a little bit later once we move towards maybe some of those bigger systems. So we've already discussed one con to graphing. Let's make a pros and cons list for graphing. So some pros, well, it's easy, right? Graphing a line is an easy skill. That's something all of us kind of said that we remember doing in our Algebra 1 course, right? Graphing lines, you probably spent a lot of time and should feel pretty comfortable about doing that. It's visual, right? You don't have to do a lot to find that answer once you've drawn your graph. You just kind of look at the picture and you should be able to see what the answer is, if there is an answer. What are some of our cons, though? Well, it's kind of time-consuming. Neatness counts, for sure. There's another, maybe less subtle con, but a really, really important one. What was that? Okay. So graphing stops making a lot of sense if we're going to start talking about 3 or more variables. 3 variables, you can still graph things in 3 dimensions. It's kind of hard to do it on a sheet of paper because it's a 2-dimensional space. So it's like, it's not really easy to see what's going on in that situation. And then 4 variables, like what's 4 dimensions look like now? It's not really have an analog to, you know, like a visual space. So yeah, that's absolutely true, and that's an excellent point. If we still want to talk about just a 2-variable situation where we have x and y's and we have things that we can put into the xy plane, there's still one more, I think, important con when it comes to graphing. So let me point this out. If we go back to this problem that we did here, we said the solution was at 5, -5, because that looked like where it was going to cross, right? What if the solution was actually 4.99, -4.99? Would you be able to tell the difference of looking at the picture? Would you be able to come up with that degree of accuracy? Not realistically, right? So the big catch is if we have decimal or fractional solutions to these, that's going to become hard to like unrealistic for us to really tell the difference between, you know, to be able to estimate a fractional or decimal answer. That's kind of where we're going here, is that the pros list, very nice, and we'll do some graphing examples, and you guys will practice this a little bit, but in terms of the go-to skill, this is one I would never use in reality. It's a good starting point because it's visual and it really kind of helps you get an intuitive sense of what's going on, and what we mean by a solution. But from a practical standpoint, actually using this process to solve anything has a lot of drawbacks. Unless you're looking for an integer solution, like whole numbered answer, it's kind of hard to come up with that. Or maybe I shouldn't say hard, unrealistic that you'd be able to come up with a whole numbered solution. So what do we want to do here? We'd like to come up with some algebraic methods that don't rely on like a graphical interpretation. And the first two of these algebraic methods we're going to talk about are substitution and then elimination. Let's talk about substitution here first, and that might be all we have time to talk about today. But talking about two methods in one day is pretty good. We did graphing, and if we can finish talking about substitution, that would be a good idea, or would be a good day, I would say. Yes, Christina. Of course. So, I'm going to return to the same system that we've used throughout as our example. And rather than describe what it is that we're going to do for substitution, because it's, again, writing the process out in words is maybe not as satisfying as just kind of seeing a careful example, that we kind of write some notes alongside. That's kind of what I'm going to do here. So the general idea is that I can't solve one equation with two variables in it. What I want to do is find a way to combine these two equations to make one equation with just one kind of variable in it. That's in general the goal throughout all of these solving system problems, is to take lots of equations and lots of variables and end up with one equation in one variable. And that we can handle solving. So one way to do that is substitution. So what I'm going to do is I'm going to pick one of the two equations. It doesn't matter. Either I'll call it equation A or equation B. And isolate one of the variables. Again, doesn't matter which variable you pick. You could isolate the x or you could isolate the y. And then we'll use that to make a substitution. So you're given a couple of choices here. First to choose an equation, and then to choose a variable. If we look at this, bless you, there's three good choices of variables to isolate and one bad choice. What would the bad choice of variable to try to isolate here be? It would be trying to isolate this 2x. Why would that be a bad idea? Great. So when I had to isolate the x, I have to divide by 2, and I'm going to end up making fractions, right? None of us like dealing with fractions. We've made that clear to me at this point. So why would I choose to do a problem in a way that's going to generate fractions? Typically my goal here, when I'm choosing an equation and a variable to isolate, is I'm going to pick one where I don't have to deal with any fractions. That's going to be my goal. Sometimes that's not possible, but in the case where it is, I definitely want to choose to not have to deal with any fractions. Is everybody okay with that? It's certainly not wrong. You'll still get the right answer, but it's like making your life harder than it needs to be, right? Our lives are hard enough. Okay. So if we're not going to pick the 2x, what one do you want to pick? Y. From which equation? A or B? A. Okay. Perfectly reasonable response. So, to get the y by itself, what am I going to do? subtract 2x from both sides, right? Everybody's okay with that? That gives me this. I'm going to refer to this as equation C, just so that I have a name to talk about it, because we have now 3 equations kind of rattling around. So what I'm going to do is I'm going to replace the y in equation B with what I know y equals. So I'm going to take what y equals, and I'm going to replace the y in equation B with that stuff. This is the substitution, right? We're substituting one thing in for another. Is everybody okay there? So I want to be clear here for a moment, because it's important that we're clear about this particular point. We used equation A to generate this that I'm going to use for my substitution. I cannot substitute back into the same equation. That's bad. Okay? You can't isolate a variable in equation A and then substitute it back into equation A. You have to use another equation. You can't substitute back into the same thing. Is everybody okay with that idea? What's going to happen if I do that substitution? I'm going to end up with 0 equals 0. That's what happens. So if you end up seeing that, it's very likely that you've made a substitution mistake, although it could just be an infinitely many solution situation. We haven't seen that happen yet. We'll see that here in a bit. So to solve this, I'm going to go ahead and distribute that negative. And then I'll combine my like terms. And then we'll add 5 to both sides. And then divide both sides by 3. And we've got one of our, or half of our answer, right? Everybody's happy with that? How are we going to find the other half of our answer? How are we going to find what y equals? I can plug x back in. Where should I plug it in? Equation A, or where else could I plug it in? I could plug it into equation C. I can't plug in equation C back to equation A, where I can't use it, plug it back into what I generated it. Right, but this x equals 5 didn't come from equation C. It came from this. We could call this equation D if you'd like. And how did we get equation D? This is C plugged into B, right? Sure. Just to, again, like, if these are notes, it should be, we want to be clear about how we're getting things, right?
Yeah.
So, happy to do that. So, where can I plug in x equals 5 to get my value for A? I can plug it in to A, B, or C. Any of those are realistic places to plug it in. Where would I not want to plug it back into? D, because D is where I got it from, right? I can't plug it back into where I get it from. That's not going to help me any. I don't know why you'd want to do that, considering D doesn't even have any Y's in it to begin with, right? The one I'm going to choose to use is going to be equation C. Why is equation C going to be slightly easier than the other two? The Y's already by itself, right? There's just a little bit less algebra to deal with. Is it wrong to do that? To do it, plug it into one of the other ones? No way! It'll be just fine. I'm just, you know, just trying to make my life easier. So again, what I did there is I took that answer, I plugged it back into equation C. You could have just as easily used equation A or equation B. It doesn't really matter. To get y equals negative 2 times 5 plus 5. And that gives me that y equals negative 5. And the way we typically write this is we're going to write it as our final answer is like an ordered pair. So we're always going to write our answers as a tuple like this. And we're always going to write the answers in alphabetical order. So like X, and then Y, and then whatever. So if the letters were A, B, and C that you solved, you'd write your answer for A, and then B, and then C. We're always writing the answers in alphabetical order. Okay with that? We have a fancy name. We call that lexicographic order. But that's not really that important. But it has a name. We don't say alphabetical order in math for whatever reason. Everybody okay with that idea? Let's do another. Because we have hinted at that it's possible that we can get infinitely many or no solutions, right? And we know what those are going to look like graphically. We described what those should look like graphically. But what are those going to look like algebraically? So let's do an example kind of each of those situations to kind of see how we're going to interpret those no solution or infinitely many solutions algebraically. So let's consider the system x plus y equals 4 and 2x plus 2y equals 9. So if we're going to do substitution, which equation would I want to work with, A or B? A would be easier. Which variable from equation A would I want to get to isolate? Sure, it doesn't really matter at that point, right? X or Y, they're going to be about the same. You guys agree with that? But certainly we can pick Y. That's absolutely fine. So to get Y by itself, we can subtract X from both sides. And that'll give me 4 minus X, or you could write negative X plus 4, whatever. Doesn't really matter. Okay? So that's our equation, C. What do we do with C? We're going to take the stuff that y equals and plug that in for the y in the equation we haven't used yet. Guess we called that guy equation. Everybody okay there? Notice I still have the 2 in front, all I did was replace the y, not any of the things attached to the y, only the y. So now I can just distribute the 2 through. And if I combine like terms, I end up with 8 is equal to 9. What is that telling me? No solution. Because does 8 equal 9? No. This is like a false statement, right? That's a lie. Everybody's okay there? All right. Let's do an example where that doesn't happen. Let me use the same stuff here. Thereabouts anyways. So this is almost the same problem, right? What's the only difference? Yeah, in equation B, we have it equal to 8 rather than 9. But everything else is the same, right? So we'll do the same thing. We'll isolate the y in equation A, just like we did previously. And then we'll take what y equals and substitute it in for the y to make our equation D. And just like before, we'll distribute the 2 through. And when I combine like terms, I'm left with 8 equals 8. What is this telling me? That's telling me this is a true statement. What this is telling me is that I have infinitely many solutions. I usually abbreviate that IMS. But we can represent those infinitely many solutions still as an ordered pair. So the way I'm going to do that is in my equation C back up here, I had isolated the y, right? I know that y is equal to 4 minus x. So what that means is I can pick an x, and to find its y, I do 4 minus x. So that is how I'm going to write my infinitely many solution. Because how many choices do I have for x? Infinitely many. Right? I can pick any x I want, but I can't have any y I want. I have to find the y very specifically. It has to be 4 minus x. So if x is 0, y would have to be 4. Right? If x is 1, y would have to be 3. If x is 10, y would have to be negative 6. Does everybody kind of see how I'm generating these solutions? And because I can do this for any number I pick for x, I have infinitely many solutions. Now, any ordered pair I want, any ordered pair I pick is not going to be a solution, right? If I pick, 1, 5, that's not a solution, right? But for x equals 1, I can find a y that is a solution, specifically 3. You guys okay with that idea? Okay. So one more takeaway here. If I look at this infinitely many solution situation, do you notice anything about these two equations? equation B is really just 2 times equation A. You guys see that? That if I take equation A and I multiply both sides by 2, I get equation B. That is enough to show that you're going to have infinitely many solutions. Now, you can certainly do the substitution and find like a true statement at the end, like 8 equals 8. But if you make that observation in the beginning, that's enough. Let's look at the no solution situation. What do we notice here? Oops. Lost a Y there. What do I mean by LHS and RHS? What do we think those are abbreviating? It's left-hand side and right-hand side. So notice that just like the previous one, the left-hand side of B is 2 times the left-hand side of A. But if I look at the right-hand side, that's not true. That's enough to show that you're going to have no solution. Or, like we did in this problem, you could do the substitution and get a false statement. That's fine as well. But those are nice little shortcuts where you don't actually have to do a whole lot of algebra to see if it's infinitely many or no solution. Usually when I'm doing this, that's the first thing I do, is I take a moment and just look to see if it's obvious that I have an infinitely many or no solutions kind of situation. And that's enough for today.